Welcome back to Studious. Today, we complete the Cartilage trilogy, having already covered hyaline cartilage, the most abundant type, and fibrocartilage, the toughest shock absorber. We now turn to the most uniquely specialized of the three, elastic cartilage. Elastic cartilage is the body's master of pliability, a connective tissue engineered not for compressive strength, like fibrocartilage, and not for widespread structural support, like hyaline, but for a single, exquisitely refined mechanical property: the ability to bend, distort, and deform under external force, and then spring back to its original shape with perfect fidelity, millions of times over a lifetime. When you fold your outer ear down and it springs back up, that is elastic cartilage. When you swallow and your epiglottis folds down to cover your larynx, then springs back to allow breathing, that is elastic cartilage. When you chew and the eustachian tube opens and closes to equalize middle ear pressure, elastic cartilage at work again. 3 locations, 3 functions, all requiring the same extraordinary biological property: resilient, repeatable, non-fatiguing flexibility.
Before we explore what makes elastic cartilage unique, we must establish the single most important property shared by all 3 cartilage types, and the one that most profoundly shapes their biology and clinical behavior: avascularity. Cartilage, regardless of type, is completely devoid of blood vessels. Not poorly vascularized, not minimally vascularized, completely avascular. There are no blood vessels anywhere within the cartilage matrix itself. Cartilage is defined as a flexible connective tissue built from specialized cells called chondrocytes, embedded entirely within a self-produced extracellular matrix. The matrix is the key. It is this dense, resilient extracellular material that gives cartilage its structural properties. But the same matrix that makes cartilage mechanically powerful also physically prevents blood vessels from growing into it. Blood vessel formation, angiogenesis, requires cells to migrate through tissue, and the dense, GAG-rich, collagen-reinforced cartilage matrix is essentially impenetrable to vascular invasion under normal conditions. In fact, cartilage actively produces anti-angiogenic factors, including chondromodulin 1, that inhibit blood vessel growth, actively preventing vascularization as a biological priority. The metabolic consequence is critical. Every chondrocyte trapped in every lacuna throughout the entire depth of the cartilage matrix must survive, function, and maintain the matrix around it using only what can reach it by slow diffusion from blood vessels in the surrounding perichondrium, or, in the case of articular cartilage, from synovial fluid. This diffusion-dependent metabolism directly determines the extremely limited regenerative capacity of all cartilage types. And for elastic cartilage, as we will see, the clinical consequences of this limitation are permanent and irreversible.
With the universal principle of avascularity firmly established, let us now place elastic cartilage precisely within the cartilage classification system, using a direct diagnostic comparison that sharpens the distinctions students need to carry into both examinations and clinical practice. The 3 cartilage types form what we call the cartilage triad, 3 specialized variants of the same fundamental tissue template, each distinguished from the others by its dominant matrix component and the mechanical property that component confers. Hyaline cartilage, the most common type in the body, is dominated by large amounts of type 2 collagen embedded in a proteoglycan-rich ground substance. Its defining property is its versatility. It is the structural workhorse of the body's permanent cartilage scaffolding, found from the tracheal rings to the articular joint surfaces to the fetal skeletal template. Fibrocartilage is dominated primarily by type 1 collagen, thick, densely packed parallel bundles of the same collagen type found in tendons and ligaments. Its defining property is extreme durability under combined compressive and tensile stress. It is found where structures must withstand intense pulling and pressure forces simultaneously, as in intervertebral discs and menisci. Elastic cartilage, our focus today, is dominated by numerous elastic fibers in addition to its type 2 collagen base. This combination of elastic fibers and hyaline-like matrix is unique to this cartilage type and is found nowhere else in the body.
Its defining property, as the name directly states, is high pliability and resilience. Elastic cartilage bends without cracking, returns to shape without fatigue, and maintains its structural integrity under repeated deformation in a way that neither hyaline nor fibrocartilage can match.
Let us now examine the three essential properties of elastic cartilage: its mechanical performance, its vascular status, and its regenerative capacity. Because understanding all three together is what allows you to truly understand this tissue, why it exists where it does, why it functions the way it does, and why injuries to it carry such serious, permanent clinical consequences. Property 1. Pliability. Elastic cartilage achieves a uniquely high pliability rating among all connective tissues. It is tough, it cannot be easily torn or fractured under normal physiological forces. But uniquely among cartilage types, it is also highly flexible. It can be bent, folded, and compressed to a degree that would crack hyaline cartilage, and that exceeds the flexibility of fibrocartilage. This combination of toughness and flexibility, without brittleness, is engineered specifically by the dense elastic fiber network woven throughout its matrix. Property 2. Vascularity. Like all cartilage, elastic cartilage has zero internal vascularity. Its metabolic life support system is entirely dependent on diffusion from the perichondrium, the dense connective tissue sheath surrounding it. This means nutrient delivery is slow, metabolic activity of the embedded chondrocytes is correspondingly low, and the tissue's capacity for internal repair is severely constrained. Property 3. Regeneration. Because of its avascularity and the low mitotic activity of its trapped chondrocytes, elastic cartilage has a severe inability to repair itself after injury. When damaged, it cannot regenerate its specialized elastic fiber architecture. The result is permanent replacement with fibrous scar tissue that lacks the elastic properties of the original tissue. This is not a minor limitation. It is a fundamental, irreversible biological constraint with direct clinical implications, with direct clinical applications.
Elastic cartilage is the most anatomically restricted of the three cartilage types. It is found at only 3 locations in the entire human body. But this anatomical specificity is not a limitation of the tissue. It is a precise expression of the principle of form following function. Elastic cartilage exists exclusively at the precise anatomical sites where high flexibility and resilience are the primary mechanical requirements, and nowhere else. Location 1 is the pinna, the outer visible structure of the external ear. The pinna has a complex 3-dimensional shape that channels sound waves into the external auditory canal. It must maintain this shape against the constant mechanical forces of sleeping on it, being pressed against headphones, being grabbed or bumped, and the minor daily trauma of normal movement. Hyaline cartilage would crack under repeated deformation. Fibrocartilage would be too rigid. Only elastic cartilage provides the combination of structural rigidity sufficient to hold the pinna's complex shape and the flexibility to withstand deformation without permanent damage. Location 2 is the eustachian tube, also called the pharyngotympanic tube or auditory tube. This tube connects the middle ear to the nasopharynx and must open and close repeatedly with every swallow to equalize the air pressure on either side of the tympanic membrane. The cartilaginous support of the eustachian tube uses elastic cartilage specifically because it requires repeated opening and closing without fatigue or structural failure. Location 3 is the epiglottis, specifically the dorsal aspect of this leaf-shaped laryngeal structure. The epiglottis must fold down over the laryngeal inlet with every swallow to prevent food and liquid from entering the trachea, then spring back to its upright position to allow unobstructed breathing, a cycle that occurs thousands of times daily for an entire lifetime.
Having established where elastic cartilage is found and why, let us now examine its internal structural hierarchy, the 3-layer organization that moves from the outer protective envelope down to the avascular core where the chondrocytes live. Understanding this layered architecture is essential for reading histological sections of elastic cartilage correctly, and for understanding how each layer contributes to the tissue's overall function. Layer 1 is the outer fibrous layer, the outer component of the perichondrium. This is the tough, mechanically robust outer shield of the entire elastic cartilage unit. It is composed primarily of densely packed type 1 collagen fibers and fibroblasts, oriented in a way that provides tensile strength and resistance to mechanical disruption. Critically, this outer fibrous layer is vascularized. It contains the blood vessels, lymphatics, and nerve fibers that make up the lifeline of the avascular tissue beneath. The presence of visible blood vessels running through this layer is a key histological identification feature for distinguishing the perichondrium from the cartilage matrix itself. Layer 2 is the inner chondrogenic layer, the inner component of the perichondrium. This is the biological nursery of the cartilage, the zone where new chondrocytes are generated. It contains chondral progenitor cells and chondroblasts in varying stages of differentiation. When the cartilage needs to grow appositionally, adding new tissue at the surface, it is from this inner chondrogenic layer that new chondroblasts are recruited. After injury, it is also from this layer that the limited repair response is mounted. Layer 3 is the extracellular matrix, the massive avascular core of the tissue embedded throughout with isolated cavities called lacunae, each housing one or more chondrocytes. This is where the elastic fiber network lives and where the tissue's mechanical properties are generated.
We have already introduced the perichondrium in the context of the structural hierarchy, but it deserves its own dedicated exploration because in elastic cartilage, the perichondrium is not merely a wrapping, but a critical physiological organ in its own right, performing two indispensable functions that the avascular cartilage matrix cannot perform for itself. The outer fibrous layer functions as the supply line. This layer is richly vascularized. On a histological section stained with H&E or a trichrome, you can identify it by the presence of blood vessel lumens, erythrocytes, and the densely woven pattern of large collagen bundles with fibroblast nuclei flattened between them. The blood vessels in this layer represent the sole metabolic lifeline of the entire cartilage. Nutrients, glucose, oxygen, and essential metabolites diffuse from these perichondrial capillaries through the fibrous layer, across the chondrogenic layer, and then through the increasingly dense extracellular matrix toward the isolated chondrocytes in their lacuna. This diffusion path is entirely passive, driven by concentration gradients, and is limited in effective range, which is why cartilage cannot grow to arbitrary thickness and why damage to the perichondrium is so clinically catastrophic. The inner chondrogenic layer functions as the genesis zone. On histological sections, this layer is identifiable by the presence of chondral progenitor cells, cells that are oval-shaped and slightly larger than fibroblasts, with a more rounded nucleus and a slightly more basophilic cytoplasm, reflecting their active protein synthesis. When stimulated, these cells differentiate into chondroblasts that migrate into the cartilage and begin secreting matrix, the mechanism of appositional growth, where new cartilage is added at the surface. This is also the source of the limited cellular response to injury, though, as we will see, that response is fundamentally inadequate to restore the original tissue architecture.
One of the most important and most consistently tested histological identification skills in connective tissue pathology is the ability to distinguish chondrocytes from fibroblasts, because both cell types are present in or around elastic cartilage, and confusing them is a common source of diagnostic error for students encountering cartilage slides for the first time. The word chondrocyte comes directly from the ancient Greek, chondros, meaning cartilage, and cytos, meaning cell. It is the true, permanent cartilage cell, the cellular inhabitant of the matrix lacunae. The defining visual marker of chondrocytes is their nucleus. It is distinctly rounded and spherical. On a histological section, this round nucleus sits centrally or slightly eccentrically within the cell, which itself occupies a lacuna, a clearly defined space carved from the surrounding matrix. The cytoplasm of a chondrocyte is typically pale staining and vacuolated in standard H&E preparations because the lipid droplets and glycogen stores that chondrocytes accumulate are dissolved away during tissue processing, leaving empty-looking cytoplasmic spaces, another key identification feature. Fibroblasts, by contrast, are the cells of the perichondrium and the dense connective tissue framework. They are immediately distinguishable by their nucleus. It is highly elongated, flattened, and oval, stretched against the surrounding collagen bundles to which the fibroblast is attached. Under high magnification, a fibroblast nucleus appears as a thin, dark, spindle-shaped or lens-shaped structure with tapered ends. The overall cell body is flat and spindle-shaped, with poorly defined cytoplasmic borders that blend into the surrounding fibrous matrix. Commit this nuclear shape comparison to memory. Round nucleus in a lacuna equals chondrocyte. Flat, elongated nucleus between fibers equals fibroblast. This single distinction will correctly identify the cellular composition of every cartilage section you encounter.
Within the elastic cartilage matrix, chondrocytes do not always exist as solitary, isolated cells. Frequently, and especially in sections from actively growing or metabolically active cartilage, you will observe chondrocytes arranged in small clusters of 2, 4, or occasionally more cells sharing a single enlarged lacuna or occupying adjacent, closely grouped lacunae. These clusters are called isogenous groups, and understanding their origin is both biologically elegant and practically useful for histological identification. The term isogenous is derived from the Greek, isos meaning equal and genesis meaning origin, indicating cells of identical common origin. The formation of an isogenous group begins with a single perichondrial cell that differentiates into a chondroblast and migrates into or is incorporated into the cartilage matrix. Once embedded in the matrix it has secreted, this chondroblast becomes trapped and transitions into a chondrocyte. Under the right physiological conditions, typically during periods of growth, repair attempts, or increased mechanical demand, this trapped chondrocyte retains the capacity to undergo mitotic division. When it divides, both daughter cells remain in the immediate vicinity, constrained by the surrounding dense matrix. Each daughter cell then continues to secrete additional matrix, slightly expanding the space around them and separating them into adjacent lacunae while remaining in close proximity. Further divisions produce groups of 4, 8, or more cells, all genetically identical and all descended from the single original chondroblast. On a histological section, isogenous groups are recognizable as nests of 2 or more round nucleated chondrocytes sitting closely together within a shared or closely adjacent set of lacunae, surrounded by the dense elastic fiber matrix of the cartilage.
The concept of the lacuna is central to understanding chondrocyte biology, and it carries a story of biological entrapment that is one of the more memorable concepts in all of histology. The word lacuna comes directly from the Latin, meaning a pit, hollow, or gap, and it precisely describes what these spaces are: cavities within the dense cartilage matrix that perfectly conform to the shape of the cells they house. Here is how lacunae are formed. Every chondrocyte was once a chondroblast, an active, secretory cell positioned at the inner edge of the perichondrium. As the chondroblast secretes matrix components, collagen, proteoglycans, glycosaminoglycans, and in elastic cartilage, elastic fibers, it releases them in all directions around itself. The matrix gradually accumulates and condenses around the cell. As it does, the chondroblast becomes progressively more enclosed by its own secretory products. Eventually, the matrix completely surrounds the cell, and the chondroblast is permanently embedded, trapped in the very material it created. At this point of complete enclosure, the cell is now a chondrocyte, and the space it occupies within the matrix is a lacuna. In a fresh, living tissue sample, the chondrocyte fills its lacuna completely. The cell and its space are a perfect fit. However, in standard histological preparations, the tissue must be fixed, dehydrated, and embedded in paraffin before sectioning and staining, a process that causes the cellular contents, particularly the water-rich cytoplasm, to shrink. The result on a stained slide is that chondrocytes appear to have pulled away from the lacuna wall, leaving a white halo or empty space between the cell and the lacuna boundary, an artifact of tissue processing that is actually a useful identification feature for cartilage in general, and elastic cartilage in particular.
The extracellular matrix of elastic cartilage performs the same fundamental mechanical role as all cartilage matrices, resisting compressive forces and bearing mechanical stress. And it does so through the same basic reinforced concrete architecture. But in elastic cartilage, this architecture is supplemented by a crucial additional component that transforms its mechanical properties entirely. The analogy of reinforced concrete is precise and useful. In standard concrete construction, two materials are combined to achieve what neither can alone. Concrete, a rigid, compressive material, excellent at bearing weight, but brittle under tension, and steel rebar, a flexible, tensile material that resists bending and cracking. Concrete alone cracks under tension. Steel rebar alone bends under load. Together, reinforced concrete withstands both compressive and tensile forces with exceptional durability. In elastic cartilage, the proteoglycan gel, composed of aggrecan complexes, glycosaminoglycans, and hyaluronic acid, all heavily negatively charged and water-attracting, functions as the cement. This proteoglycan gel withstands compressive forces through the hydraulic mechanism of trapped water pressure. When compressed, the negative charges resist each other electrostatically, while the water is pressurized, distributing load and resisting deformation. The type 2 collagen framework functions as the rebar. The collagen fibers bear the tensile and shear mechanical stresses, preventing the matrix from tearing apart when subjected to lateral or bending forces. In elastic cartilage specifically, a third component is added to this reinforced concrete system: the dense branching elastic fiber network woven throughout the matrix, which we will examine in dedicated detail in the next slide.
We have now arrived at the single molecular feature that makes elastic cartilage fundamentally different from all other cartilage types, the component that earns it its name and defines its unique mechanical identity: the dense, branching network of elastic fibers saturating its extracellular matrix. What makes elastic fibers different from collagen fibers? The answer lies in their molecular composition and architecture. Elastic fibers are composed primarily of elastin, a remarkable protein built from cross-linked tropoelastin monomers. The cross-links between tropoelastin molecules are formed by a specific enzyme called lysyl oxidase, creating a three-dimensional network of covalently bonded protein chains. The elastic network has a rubber band-like molecular architecture. When stretched or deformed, the protein chains unfold and extend. When the deforming force is removed, the crosslinks pull the chains back to their original coiled configuration with no energy input required. This passive elastic recoil is essentially perfect. Elastin can undergo millions of stretch and recoil cycles without fatiguing, without losing its recoil properties, and without permanent deformation. In hyaline and fibrocartilage, elastic fibers are present only in small, trace quantities. In elastic cartilage, they are present in extraordinary abundance. The matrix is saturated with them. Under special staining with orcine or resorcin fuchsin, which selectively stain elastin, the elastic fibers of elastic cartilage appear as a dense, branching, interconnected web, thick fibers branching into thinner ones, weaving between and around the chondrocyte lacunae in every direction simultaneously. It is this highly interconnected elastic web that gives the tissue its unique pliability, and it is the irreplaceable loss of this web when the tissue scars that permanently destroys the flexibility of injured elastic cartilage. We have established that all cartilage is avascular. Now, let us examine what that actually means at the cellular level, because the metabolic reality of living and functioning inside an avascular matrix is one of the most remarkable biological adaptations in the human body, and it has direct consequences for how elastic cartilage ages, responds to mechanical loading, and responds, or rather fails to respond, to injury. Blood vessels cannot penetrate the cartilage matrix. The only mechanism for nutrient delivery is diffusion, the passive movement of molecules down their concentration gradients from an area of high concentration at the perichondrial blood vessels to an area of lower concentration at the chondrocyte within its lacuna deep in the matrix. Diffusion is inherently slow, distance-limited, and non-selective. The effective diffusion distance through cartilage matrix is limited, typically no more than a few hundred micrometers for large molecules like glucose under ideal conditions. This is why cartilage cannot be thicker than a certain maximum. Beyond that thickness, central chondrocytes would be beyond the effective diffusion range and would not receive sufficient nutrients to survive. The direct biological consequence of this diffusion-dependent nutrition is that trapped chondrocytes, already isolated within their lacuna, already deprived of direct vascular contact, exhibit exceptionally low mitotic and metabolic rates. Their cell cycle is essentially arrested. They divide extremely rarely, if ever under normal physiological conditions. Their metabolic activity is reduced to a maintenance level, producing just enough matrix components to replace what is degraded and responding slowly to mechanical loading signals. This metabolic quiescence is the central reason why elastic cartilage, and all cartilage, has such limited regenerative capacity. There are almost no available cells capable of rapid proliferation and matrix synthesis in response to damage. The metabolic reality of the previous slide leads directly to the most clinically important fact about elastic cartilage: its fundamental, permanent inability to regenerate after significant injury. When elastic cartilage is injured, whether through acute trauma, surgical incision, chronic pressure, or inflammatory disease, it cannot repair itself the way vascularized tissues like muscle or bone can. There are 3 biological locks that prevent self-repair. First, the chondrocytes are immobile, permanently trapped in their lacunae within the dense matrix, unable to migrate to the injury site. Second, they have an extremely low metabolic and mitotic rate. Even if signaled by injury, they cannot rapidly proliferate to produce new cells. Third, there is no internal vascular supply. Even if the cells could proliferate, there is no mechanism to deliver the oxygen and nutrients needed to support a large-scale repair response. When a significant injury penetrates the elastic cartilage matrix, the only repair response available is from the perichondrium. The perichondrium mobilizes its fibroblasts and chondroblasts, the cells of the chondrogenic layer, and sends them into the wound site. However, these cells are not producing specialized elastic cartilage with its complex elastic fiber architecture. Instead, they produce dense connective tissue scar, a generic fibrous repair material made primarily of type 1 collagen, with no elastic fibers, no chondrocytes in lacunae, and no proteoglycan-rich matrix. The result is permanent functional impairment. The injured area is filled with rigid scar tissue that lacks the pliability and resilience of the original elastic cartilage. The ear that was deformed does not fully recover. The epiglottis that was damaged may no longer fold and spring back correctly. The fundamental architectural identity of the elastic cartilage is irreversibly lost.
We close with the complete elastic cartilage blueprint, the integrated synthesis of everything covered in this video, consolidated into the 3-domain summary that serves as your master revision reference. Domain 1, form and location. Elastic cartilage is found at 3 anatomical locations: the pinna of the ear, the epiglottis, and the eustachian tube, all selected by the same functional criterion: the need for high, repeatable, non-fatiguing flexibility. Its matrix consists of chondrocytes trapped in lacunae, supported by a dual structural framework of type 2 collagen and, uniquely, a dense web of branching, interconnected elastic fibers composed of cross-linked elastin. This elastic fiber network is the single defining feature of the tissue and the direct molecular basis for its mechanical identity. Domain 2, structural matrix. The tissue is organized into a 3-layer hierarchy: an outer fibrous perichondrial layer providing structural protection and the vascular supply that diffuses nutrients inward, an inner chondrogenic layer serving as the cellular nursery for chondroblasts and limited repair cells, and the massive avascular extracellular matrix core where the chondrocytes live. Within the matrix, chondrocytes may appear solitary or in isogenous groups, clusters of genetically identical cells descended from a single original chondroblast. Domain 3, clinical reality. Elastic cartilage is entirely avascular, maintained exclusively by perichondrial diffusion, metabolically quiescent, and fundamentally incapable of full regeneration. Injury produces fibrous scar tissue rather than true cartilage replacement, permanently destroying the elastic properties of the affected structure.
This permanent regenerative limitation is not a flaw in the design. It is the price of the extraordinary mechanical specialization that makes elastic cartilage the body's most pliable connective tissue. Thank you for watching MedStudious.